The fable of the sandcastle. Does the second law of thermodynamics predicts the end of everything? My name is Levi. So you have here the second law of thermodynamics that predicts that entropy always increases for isolated system. And by isolated system, you have that this system does not change matter and energy with its surrounding. So you have a classical example here that a gas inside a container occupy part of the container, and with time this gas will expand and its entropy will increase over time. Entropy is the measure of disorder. So the second law of thermodynamics predicts that entropy always increases in isolated system. You have other examples. So this is a clip from the BBC television series Wonders of the Universe. Show a castle, a system that's slowly disintegrated by the action of the wind. So my question here is the sandcastle an isolated system? You can pause this video and watch this video of the sandcastle on YouTube and take your own conclusions, and then you can regret here. Examples found in the universe. The sandcastle is not an isolated system because it undergoes wind action that carries sand particles in and out of the system. So just to remember that isolated system does not change matter and energy. The sandcastle is an example of an open system. So it's a misconception to compare with an isolated system. And it's very difficult to find in the universe an isolated system. There are other examples of open system in the universe, which the entropy can decrease over time, like the formation of a snowflake and the accretion process. So you cannot find examples of isolated systems, just open systems. Here the snowflake formation, you have a snow crystal that have highly organized, the molecules are arranged in very organized structure. You have the water vapor with high entropy converting ice with low entropy. So you have here an example of an open system that decreased the entropy over time. You have here the accretion process. The accretion process is the formation of a planet. You have gravity force that clump the stardust together, forming a highly organized body giving rise to a planet. So you have an open system. The gravity is attracting matter and it's forming a planet. So another example of an open system. So the universe, you will find only open systems. You have, in the case of the sandcastle, an open system that increases in entropy. And you have the example of a snowflake formation that will decrease in entropy. So I challenge you to give me an example of an isolated system in the universe. There's no example. And open system, you have several examples on the universe. You have stars, planets, living beings, and even sandcastles that are open systems. Even if a system is arbitrarily delimited, a notional system, it's not possible to consider an isolated system because all the objects known in the universe are open systems. And what about the fate of everything? The second law predicts the fate of everything. It's not a good model for this. You have the universe. It's not a homogeneous system such as gas. So here you have 95% of the universe is still unknown, corresponding to 23% of dark matter and 72% of dark energy. The non-ordinary matter is no more than 5%. And the fate of the universe is governed by gravity and the density of matter. You have three possibilities here for the fate of the universe. An open system that where the universe will expand forever, the flat universe where the expansion will slowly decrease, and you have the big crunch here. The universe will collapse with its own gravity. Gravity will influence the at macroscopic level. You have here an example of sedimentation process. You have sand grains inside water, and it's occupying all the container. And with time, the particles will accumulate here on the floor of the container. So you have the decrease in entropy here for objects that has considerable size, like a sand grain. Even if you consider here an isolated system, gravity will act on it, the body, even in an isolated system. And just to compare here, you have the gas expansion that's initially occupying part of the container, and the gas expansion will occupy all the container. The sedimentation process, here the particles will lay down here and will form a very organized layer of sand particle. So the difference here is the size of the body, the object of study. You have a gas that does not have influence of the gravity, if you consider a small container, and you have the sedimentation process that will decrease in entropy over time, even in isolated systems. And why is that? Because the gas has it's free to move inside the container. You have the kinetic energy here, and you don't have, like the solids in solid states, intermolecular bond that clump the atoms together and form a body with considerable size that the gravitational force will influence in that body. So that's why at macroscopic level, the model of thermodynamics does not fit very well. For gas, it's a very good model because you have the free movement of molecules inside the container by the kinetic energy. And just to see that the decrease in entropy here, you have sand particles that different size, and you have very organized layers of sand particles according to its particle size. So again, if you consider that an isolated system, the gravity will act on it because it's a macroscopic body. And the forces of the nature will act on the bodies and will not let the bodies float away. So you have the gravitational force, electromagnetic force, weak force, and strong force. Without these fundamental natural forces, all the matter in the universe will fall apart and float away. So in the case here where the gravity will clump the bodies together and decrease in entropy in open systems. The evolving universe. So here you have the universe that's expanding, but perhaps it's expanding. The complexity of the universe always increased over time. The organization of very discrete objects of the universe emerge over time. You have here in the beginning a soup of particle and energy, an homogeneous system. So over time, galaxies emerge, planets emerge, living beings emerge, and you have the expansion of the universe and the formation of many, many, many open systems that decrease in entropy over time, that get a high level of organization over time. Even considering the universe as an isolated system, it does not behave like a gas inside a container. The universe is not homogeneous like a gas. And it's very difficult to predict the end of several open systems. So if you take the second law of thermodynamics, that predicts that entropy always increases over time in an isolated system, you don't see this in nature, in the universe, because the universe is made of several open systems. Comparing such a complex system like the universe with a gas inside a laboratory container needs a careful analysis, because there is no isolated system known in the universe. The laws of thermodynamics are good models for gases, but it's very imprecise in predicting the fate of our universe and the behavior of macroscopic bodies that's influenced by gravity. The universe does not show isolated system, only open system, and you have open system that can decrease in entropy over time, like the example of snowflake formation, accretion process, and several other examples that you can give to show that the universe is made of several open systems that can increase or decrease in entropy over time. Thank you very much, and if you want to read a little bit more about this, you can email me and I will send you an ebook that's discussing about this very interesting field of science. Thank you very much.